Hello, students. Putting together this little video to explain the birthday problem, simply to circumvent any problems you might have with Teams, with things freezing and whatnot. So this will be up on YouTube, and of course, it is on YouTube now. See, I'm making it in the past. You're seeing it in the future. You're actually seeing it in the present, but because I'm living in the past right now, the present is the future to this me. But probably next time I see you, the present that you're living right now will be the past. It's so complicated. Um, at any rate, in order to understand the birthday problem, what I've tried to do is create this idea of taking a multiple choice test and uh, and seeing can you get a zero on it. So I'm going to modify the multiple choice test thing down to being 4 options per question. Let's say there's 5 questions. Okay, so there's 4 things you could do for number 1 and 4 things you could do for number 2. So if you're just looking at answering number 1 and number 2, there's actually 16 different options. There's like A for number 1 and A for number 2, A for number 1 and B for number 2, A for number 1, C for number 2, etc. So you have all the 4 options that go with number 2 with A for number 1, and all the 4 options go with number 2 with B for number 1, etc. So you have 16 options. When you move on to number 3, now we're up to 64 different ways to answer. When you get to number 4, there's 128 different ways to answer. What's happening here is we're doubling, going from 4, actually multiplying by 4 to 16. 16 times 4 is 64. Oh, so 128 is wrong, I'm sorry. And then 64 times 4 is 256. And 256 times 4 is 1,024. So if you have 5 questions, there's actually 1,024 different ways to fill out an answer sheet, as long as you're answering every single question. So what we're going to do is we're going to say that every question gets answered. One of those 1,024 is getting all 5 of them right. But if you think about how can we be wrong? Well, there were 3 ways to get number 1 wrong, and 3 ways to get number 2 wrong, and 3 ways to get number 3 wrong, and 3 ways to get number 4 wrong, and 3 ways to get number 5 wrong. So we're doing 3 times 3 times 3 times 3 times 3, or 3 to the 5th. So let me think this through. 3 to the 4th I know is 81 because that's 3 squared. So, okay, so there's 243 different ways to be completely wrong and to get all 5 wrong. So 3 to the 5th is 243. That's 81 times 3. So I'm going to use this little device right here, although I don't actually have to. I'm going to consider that 243 is kind of close to 250, and 1024 is pretty close to 1,000. So we're talking about 25 out of 100 to 25%. So if I gave a 5-question test to a bunch of students, and nobody knew any of the answers, it was just random, like the experiment we did the other day, then maybe 1/4 of them would get no credit, but 3/4 would get something right. Okay, so the idea here is that even though the odds of being right on any one item are kind of slim, so the odds of being wrong are pretty high, the odds of being wrong over and over and over and over again are start to come down as you get more and more and more trials. So to bring this over to the birthday problem, we change the fraction. So instead of being 3/4 of the time you're wrong on the test, now 364 out of 365, that's the odds of not having a birthday match. So you take any pair of people and say, hey, do you guys have the same birthday? Chances are they don't. They probably don't. But when you have more and more and more and more pairs, then the odds of there being a match start to go up. And the odds of there being no match then, of course, are coming down. That's actually the proper way to think of it, is that you're taking 364 out of 365. And you take that fraction, start raising it to higher and higher and higher powers, and see what it takes for that to come down below 50%. A way of thinking about this, let's suppose you have 5 people. What I'm going to do right here is I'm going to pretend that we have a person here, and one here, and one here, and one here, and one here. So we're trying to create the idea of a pentagon existing, okay? How many different pairs can you create? Well, if we connect each person to each other person, we get this little network map here that should show that the first person can be paired with any of the other 4, and the next person can be paired with any of the 3. We should wind up with 10 as this answer. And actually in this picture, it would be the pentagon with its diagonals being 10 different pairs that can be created. So if we had 10 people, the odds of a birthday match, or the odds of a not birthday match, would be 364 out of 365, that quantity raised to the 10th. Use this little device here to find out what that is. So I'm just putting in open parentheses 364 divided by 365, close the parentheses, use the caret to go to a power, and I'm putting a 10 up there, okay? And I'm finding 97.29 or 97.3 or 0.9729. So 97.3% chance of there being no match. So what has happened is the odds of there being a match has come up to almost 3%. Now, if I go back and take this thing, if we go to 6 people, now we have another 5 pairs that could happen because this new person that's been added can be paired with any of the other 5. So now I'm going to go to the 15th power. And when we do that, we have 95.96. So we have about a 96% chance of no match. Therefore, a 4% chance of there being a match. All right. Now I'm going to go and we're going to add one more person. And so instead of using 15, we're going to go to 21 pairs happening. All right. And we have 94.4. So that's percent chance of no match, and therefore 5.6 chance of there being a match. So the match is becoming more and more and more likely. All right. Now, the question that we have to answer here is how many people do you have to have before that exponent gets to be big enough that the odds of no match drops below 50%, and that means the odds of a match comes above 50%. All right. So what I'm going to recommend is that you just put those numbers into a calculator and start looking for different exponents. And what you can do is you can throw in, a couple hundred or 300 and see what happens. Actually, I'm going to do that right now. I'm going to put in 200 as an exponent. All right. Now this is not 200 people. The exponent of 21 was 7 people. So I'm going to put in 200 here, and I got a 57.7% chance of no match. Now I'm going to do it again, and you should know the calculator trick of not typing it in again. You just highlight what you did, hit enter, it shows up again in editable form. So now I'm just changing the exponent to a 3. Now we're at 43.9. So an exponent somewhere between 200 is going to be the right exponent to use. All right. Now then we have to figure out, well, what's the number of people that's going to get us close to that exponent? And that's the question we're going to be answering when we meet later, because with the block schedule thing, we're not meeting on the same day. So that's that, and I hope you enjoyed this little explanation, and that how to use the machine to begin solving this problem makes a little more sense. Have a great day.